of galactic applications of simulation of magnetic fields in compressible flows. And actually, you are recording this, right?
Yes.
So Mara will be able to see.
Yes.
Okay, good. So the plan is the following. The sources of the cell turbulence will be first discussed. And in my lectures, I discuss supernova explosions. But here, the other sources will also be introduced, and their relative importance will be discussed. And among the important physical processes in the interstellar medium is thermal instability, which will be discussed here in quite appropriate detail. And then the multiphase structure resulting from it will be discussed. And then supernova explosions will naturally come to the scene. And then we shall discuss another important instability, the magnetorotational instability, which can also be important in galaxies and contribute quite interestingly to interstellar turbulence. And then all this will be discussed in the context of galactic dynamics. So we start with what? Source of interstellar turbulence. First of all, the galaxies are get differential. Shear flows can be unstable, and that the part of the kinetic energy of the shear flow can be converted to turbulent energy. This is not a trivial process. It's not easy to do that. For example, it's known that it's a Rayleigh criterion of stability. The rotation such that d by dr of omega r squared is larger than 0. Omega r squared is the angular momentum per unit mass. If this is true, then the differential rotation will be stable. And it will be difficult to convert its energy into turbulence. And this is true for galactic disks. In galactic disks, if rotation curve is flat, omega is proportional to 1 over r, then omega r squared grows as r. And definitely this flow should be stable with respect to Rayleigh's criterion. A similar problem was a major obstacle in the development of the physics of accretion disks, where omega decreases in a Keplerian way as r to the power minus 3/2. And again, the accretion disks are stable with respect to Taylor's Rayleigh's criterion. The result was that it wasn't clear what drives turbulence in accretion disks. But still, differential rotation can be potentially important mechanism of driving turbulence in differential rotating disks, including galaxies. And then we shall discuss magnetorotational instability, which tells us that this mechanism makes even flows stable with respect to this criterion, unstable, if only there is a magnetic field arbitrarily weak. It's a very interesting, very beautiful physical phenomenon. Then, briefly, Parker instability is another instability which is specific to galactic disks and can be important for driving turbulence. There are two versions of Parker instability, in fact. And Parker himself, Gene Parker, was carefully distinguishing the two. One is just magnetic buoyancy instability. If I have magnetic field, say horizontal magnetic field, homogeneous, in the gravity field, G is directed that way, this is magnetic field. And if the system is in hydrostatic equilibrium, z is equal to 0 is here, grad rho is directed that way. So density increases downwards. Because of hydrostatic equilibrium, and you have a flux rho, say, intense flux rho. Then magnetic pressure plus gas pressure here should be almost the same as at the upper layer, just a smaller difference. This means that there will be less gas within the flux tube because of the pressure balance. If there is less gas, the tube is light and it rises buoyantly. The result will be that this tube will change its shape, and undulations of this sort will occur. So it will be buoyant, it will rise up. This is what is known as the magnetic buoyancy instability. It's not Parker instability. What Parker suggested is the following. If in addition you have cosmic rays in the system, cosmic rays is a relativistic gas and it's weightless. Basically the energy is large, but the mass density is very low. The particles are so energetic that they provide significant pressure and significant energy with negligible mass. Then this will make everything even stronger. If there are cosmic rays here, and cosmic rays like to be where magnetic field is, then the density deficiency here will be even stronger. And this will amplify this magnetic buoyancy instability very significantly. So, and Parker, in his papers, always insisted that the Parker instability is the one involving cosmic rays. In contrast to the just normal magnetic buoyancy. It's a very important instability. The problem with this instability is that the physical mechanism is very clear. You can calculate all the parameters, you can know the most unstable wavelength, everything is fine. But loops like this, I think, well, there were some suspected objects, but they were never observed in the interstellar medium. It's surprising. The mechanism is very simple. It's not impossible to imagine that it won't work. This means that probably this instability is somehow suppressed in the interstellar medium. One of the ways to suppress it is to remember that this medium is turbulent. And turbulence can really hinder the development of this instability. But it's an open question. Why these spherical loops are not observed directly, readily observed at least into the interstellar medium? It's a very interesting question. Then there is stellar forcing, stellar winds, radiation pressure, supernovae. These I already mentioned in my lectures. Then there is thermal instability, another interesting instability. I will discuss it. Marit will discuss it. And gravitational stability. At the end of the day, the interstellar gas, becomes, if self-gravity becomes important as soon as the density becomes high. If it's compressed to high density, above what? 10 to the 5th particles per cubic centimeter. Then it becomes self-gravity becomes important, it becomes gravitational instability, and of course it helps to form stars. The most of the energy is supplied by supernovae. In the regions where star formation is strong, supernovae provide sort of 3/4 of the turbulent energy. And 1/4 comes from the other sources. But supernova activity, star formation activity, ends at a certain radius within the disk. If I have the galactic disk here, then it's clear that, and this is the axis of rotation, axis of symmetry, it's clear that everything decreases outwards, right? And there will be always some radius where gas density becomes so small that star formation becomes very low. Star formation rate becomes very, very low. In the Milky Way, this happens at the radius of 16 kiloparsecs. The number of supernova remnants drops to virtually 0 at this radius. So there are no supernovae beyond this radius. But it is exactly where the magnetic rotation and other instabilities can be important in driving turbulence. And I will discuss at the appropriate place that there is some evidence that even beyond this radius, there is turbulence. Turbulence is maintained somehow. And moreover, perhaps even large-scale magnetic fields are maintained here. It's another unsolved, not very clear, but important question. And due to all these contributions to dynamos, there can be, in galaxies, different dynamo regimes in different parts of galaxies, or in different galaxies. It makes all this additional physics makes the picture much richer in terms of their consequences for the dynamic action for magnetic fields. Thermal instability. This is an instability discovered by George Field in 1965, and then they published with Goldsmith and Hadding in 1969 a very influential paper where they noticed the following: that gas in the interstellar medium is in the state of, probably it must be in the state of thermal equilibrium, right, if it's a generally steady state. The gas is constantly heated by various sources. The main source of heating is the ultraviolet emission of stars. Per unit volume, ultraviolet emission, how the gas is heated. The atoms absorb ultraviolet photons, which makes the gas hotter. Per unit volume, the heating rate will be proportional to density. Because the more atoms you have to absorb this light, the more energy will be absorbed. So the heating is proportional to density. Cooling, simultaneously the gas cools down. It cools down because it radiates energy in the form of electromagnetic waves. It happens when two atoms collide. When they collide, they can emit some extra energy. Because cooling depends on the binary collisions. The cooling rate depends per unit volume. Is proportional, is functional temperature of density squared. So the net cooling or heating rate per unit volume will be proportional to some function of T, temperature, because of course it would be important to know at what speeds the two atoms collide. This makes it temperature dependent. Binary collisions make it rho squared. It's the cooling rate minus heating rate. So this is the net cooling rate. Now this is per unit volume. Per unit mass, to get the expression per unit mass, you divide by rho. So unit mass will cool proportionally to the density, and it will be heated at a constant rate, independent of density. This is what we have here. This is the net cooling rate per unit mass. Now, imagine that this cooling rate is less than 0. Less than 0. The derivative less than 0. D by dt. By temperature. Less than 0. So, we have a parcel of gas. It will, suppose that it loses some energy. It cools down. If it will cool down, this means that L is negative, right? L is negative. It cools down. If del by dt is negative, if it will cool down, temperature will decrease, and therefore the magnitude of L will increase. It will start cooling down even faster. And faster and faster and faster. This creates instability. So if only del by dt is negative, the system is unstable. A parcel of gas which cools down due to random reasons, random, starts cooling down further and further. If it warms up, it will start getting warmed up further and further. And the result is that the homogeneous gas, if only it is unstable, will be split into two stable phases. One cool and dense, the other hot, warm, and dilute. There are several regimes of this instability. For example, this can happen for constant density, is isochoric process, or isobaric process if it happens with constant pressure. This is most important applications, because in the interstellar medium, on average, you have pressure balance. The pressure, at least horizontally, is almost constant. If not, there would be sound waves propagating in all directions, so the pressure equilibrium is restored. If there are no average motions, pressure must be constant. And there is also an isentropic version of this. So this isobaric version of this instability is most important, and this is what was considered by George Field. It's the same George Field who was a supervisor of Eric Blackman, who contributed so significantly to dynamo theory by suggesting that the magnetic helicity conservation can be important for nonlinear dynamo action. It is the same George field. So, what is plotted here is the dependence, are the contours of this cooling rate, this one, per unit mass, for the interstellar medium. So, you know the chemical composition of interstellar gas. If you know enough of atomic physics, you can calculate this cooling rate, lambda of T, as a function of temperature, for the chemical composition of the interstellar gas. So, this function can be, knowing what is the stellar population of galaxy, you can calculate how many ultraviolet photons they emit and how rapidly the gas can be heated. So this cooling function can be calculated from almost first principles. It's basically atomic physics and then stellar structures. And then you can plot in the raw T plane the contour where this L must be equal to 0. This is how it looks. So above this curve, L is positive. Beneath this curve, L is negative. So cooling here, heating here. And this dashed line corresponds to the product T times rho equal to a constant pressure. Constant thermal pressure is the line where rho times T equal to a constant. So T is proportional to 1 over rho. In log-log plot, it's a straight line. And we see here that the gas will be stable. This gas will be unstable. This gas will be unstable. This gas, which has higher density and cooler, will cool down further. This gas, which has higher temperature and lower density, will be heated up further. And all this gas will be unstable. So ideally, there will be no gas in the interstellar medium because of thermal instability in this range of temperatures and densities. If the log T is 10 to the 4th kelvins, and this is 10 to the 2nd, 100 degrees Kelvin and 10,000. This is why the warm gas in all galaxies has a temperature of 10,000 degrees. This is why the speed of sound in all galaxies, all radii, is 10 kilometers per second. This is why the turbulent speed is of the order of 10 kilometers per second in virtually all galaxies and virtually all positions. Because this temperature is controlled by atomic physics. It's controlled by thermal instability and the cooling and heating rates. Beautiful, isn't it? So this was the achievement, the result of George Field, who showed that, and this explained the existence of the warm gas at a temperature of 10,000 degrees and the cool gas at a temperature of 100 degrees. If you put densities here, this will have the density of 100 particles per cubic centimeter. And this density will be of the order of 0.1 particles per cubic centimeter. So the pressures will be the same. 0.1 times 10 to the 4th is 10 to the 3rd. 100 times 100, 10, then 10 particles per cubic centimeter. So this is the line where rho times T is constant. So if this is 10 particles per cubic centimeter times 100, is 10 to the 3rd. The pressure in this unit is 1,000. And likewise here, 0.1 particles per cubic centimeter times 10,000 gives you the same pressure in this unit of 1,000.
And what, is there a similar stability for the hot gas as well?
No, no. This depends on the cooling curve. But, oh yeah, there will be instability beyond million degrees, where the cooling curve starts decreasing. I think there will be some such. But it's relatively easy to do. You just calculate this function, plot it. For example, there are various ways to present it. It can be pressure as a function of temperature, any two independent thermodynamic variables. And then It's just making this plot and looking at what you have. Is it stable or is it unstable? Yes, please.
Has this been observed in a plasma in the lab? Can you do any of this? Or?
I don't know, but I would guess yes. Why not? Why not?
It's a fascinating phenomenon.
Yeah. Excellent, isn't it?
Yeah.
I don't know about laboratory, but I won't be surprised if the answer is yes. But I don't know.
Because you create the right corrections, and suddenly, out of instability, then you will form spontaneous hotspots surrounded by a core medium.
And cool dense regions. So, there was a series of papers published in about 10 years ago. There was a burst of activity about turbulence driven by this instability. It's a sort of a thinking by analogy, right? We are used to the idea that instabilities can drive turbulence. Another instability, thermal instability, will drive turbulence. Let's study turbulence driven by thermal instability. Wrong. Thermal instability cannot drive turbulence on its own, because turbulence is always constant injection of energy, which is then converted into heat. And instability can drive turbulence only if the system is kept in unstable state, right? Otherwise, the instability only acts once and then saturates and the system becomes stable. So thermal instability results in the development of two stable phases. And unless there is something which makes the system unstable again, that is, mixes the two phases together, warms up the cold gas, cools down the warm gas, warms up the cold gas, and cools down the... So the cold gas should be warmed up, the warm gas should be cooled down, for the system to become unstable again. Unless there is a physical process which does it, the instability cannot drive turbulence. Well, theoretically there is such a process, half formation. These cold regions will eventually condense further and start making stars. And the stars will disperse these clouds. But directly, this doesn't happen. So thermal instability only acts once. And still there was quite a number of papers discussing turbulence driven by thermal instability. I think the idea is wrong. And there was a paper of Axel Mare and Tony Mee. Tony Mee was a PhD student in Newcastle at that time, who demonstrated clearly that self-sustained turbulence cannot be driven by thermal instability, but still it can affect the dynamo action. This is an example Mare shows. So the yellow curve here, this is time, this is RMS velocity. If there is instability, RMS velocity will be non-zero, right? There will be some motions involved when the gas separates into two phases. So yellow curve, orange curve. So this is thermally unstable, and black is thermally stable, right? So not surprisingly, in thermally stable case, the velocities are lower. So this difference in kinetic energy is the contribution of thermal instability. Both runs have forced turbulence. So RMS velocity in both runs differs from zero. So it's driven turbulence. But on top of the turbulent driving, there is a thermal instability on the yellow curve and no thermal instability on the black curve. Now this is RMS magnetic field driven by the fluctuation dynamo in the two cases. We see that thermal instability suppresses dynamo action, and quite significantly. You look at the difference in the growth rates. The growth is quite steep in the stable case and very shallow in unstable case. And the saturated levels are different. I guess the reason can be the following. First, why the RMS magnetic field is so different. Just because in the unstable case, most of the gas, most of the mass of the gas, is in dense clouds, which don't contribute directly to dynamo action. Dynamo action occurs in diffuse gas, which is left. and very less gas left. So you have lower kinetic energy here. But it's all my speculation, because I don't know well these results. So what I'm saying can well be wrong. But Murray will see that, and hopefully she will somehow correct me if I'm wrong. So I will not speculate further, but this is the result. That the dynamo action in unstable, thermally unstable medium can be significantly different from the one in the thermally stable. And here is the structure of the solutions. This is an unstable solution, and this is stable. There's a slice in the xy plane through a three-dimensional domain. The dashes show magnetic field, and color, I would guess, shows either temperature or density. But it doesn't matter. Since the pressure is constant, pressure and density are uniquely related to each other, so it doesn't matter whether it's temperature and density. In the unstable case, there are, you see this, this is the cool, dense phase. You see these globes of dense gas. And this is much the region, the domain is much more homogeneous, the gas is much more homogeneous in the stable case. And magnetic field here is what? So, thermally stable case exhibits very clear density magnetic field correlation. In thermally unstable flow, the densities aren't clearly correlated. Let me make a comment on this. This refers to what we discussed about the behavior of frozen in magnetic field. If magnetic field is frozen into the gas, we expect that B, magnetic field, will scale with gas density alone. It will be some power n. For spherically symmetric collapse, this n is equal to 2 steps. So, for frozen in magnetic field, we expect a very clear correlation between B and n. If you make a scatter plot of B versus rho, you will get something like that. There will be some scatter, but you will get a clear correlation. And as far as I understand, the statement here is that here this correlation is more or less well pronounced. Here it is not. My interpretation of this is the following. Without instability, this is just, well, driven turbulence, and to the lowest approximation, magnetic field is indeed frozen into the gas. So you observe this correlation. But in the case of instability, there is a much stronger condensation of gas, so that in each individual cloud, you will have strongly distorted magnetic field. If magnetic field originally, say, was homogeneous, and there was a cloud which then condenses, then it's, for example, to this size. It's clear that it will drag magnetic lines together with it, so magnetic lines will be strongly distorted, and they will slip out from the cloud. So this will make flux freezing much more questionable. So more flux isn't frozen here just because of strong compression. So you naturally can expect that this dependence of B on density will not be that strongly pronounced as in the stable case. Here, homework. We since a long time ago, several years now, maybe 2 or 3 years, we have been working on a paper which is practically finished, discussing these processes also in application to molecular clouds. It's my fault that the paper hasn't been submitted yet. So, Murray, I will do it. Yes.
May I make a short comment?
Of course, yes.
I did simulations of thermal instability, and I found a nice 2/3 correlation between density and magnetic field. So
yeah.
I don't quite agree with this statement.
It depends on the parameters. We should ask Mara what was the magnetic diffusivity in this run. It was high, then my explanation works. If it wasn't, I should think again. This is probably why Mara says that I shouldn't just write the draft. First, there should be some homework. Agree. It depends on parameters.
I might have to look into these results again.
But on the other hand, it would be really interesting to find out what happens in real interstellar media with the real extreme values of all these diffusivities and bipolar diffusivities and stuff like that. It's an important question. And it's okay. We can discuss it later. It's interesting. Now, supernovae. Stars which have the mass of about 20 solar masses, their lifetime, because they're so massive, is very short, million years. They explode, releasing enormous energy into the stellar medium. And this energy is injected as mixture of thermal on different phases of the supernova expansion. It's a different mixtures of thermal energy and kinetic energy. It heats the gas in the interstellar medium, compresses it, accelerates it, and but most of this energy, it also accelerates cosmic rays, which are also accelerated in supernova remnants. But most of this energy is radiated away as electromagnetic waves. In an absolutely uniform medium, the blast wave will be perfectly spherical, right? It will be perfectly spherical, expanding blast wave. In homogeneous medium, of course, it will not be any longer perfectly spherical, and there is, for example, an interesting solution for the expansion of the blast wave. The first solution explaining this expansion was obtained in 1949 by Sedov and Taylor, independently, in America and Soviet Union. And it's not a coincidence. Both countries were involved in the development of nuclear arms. And these solutions describe the expansion of the fireball created after the explosion. So this solution will be presented later. Then I will present later. Okay, fine, let's continue. And then, since part of this energy is converted to kinetic energy, about 10% of this energy is converted into kinetic energy of the interstellar gas. The result of this activity is the random, or perhaps even turbulent, state of the interstellar gas. An additional outcome of this is that supernovae create and maintain a hot gas. The point is that I removed this expression for the cooling rate. Let's restore it. And that cooling rate per unit gram is proportional to a function of temperature times rho minus W. A very dilute gas with low density will cool very slowly. Supernovae create gas of the temperature of million degrees Kelvin, which has very low density, 10 to the minus 3rd particles per cubic centimeter. The result is that this gas cools very slowly. And before it can cool down to normal temperatures, there will be another supernova going off in the neighborhood of any position, and more hot gas will be created. The result is that these bubbles of hot gas created by supernovae, they merge together and form a pervasive hot phase of the interstellar medium. This phase was discovered in the 70s, when the first ultraviolet observatories were launched to the orbit. Ultraviolet is absorbed by the Earth's atmosphere. This is why we don't have, all of us don't have skin cancer, just because the atmosphere protects us from the ultraviolet emission of the sun. Therefore, to observe in ultraviolet, you have to go beyond the atmosphere to the orbit. This was done in the 70s, and immediately what was observed were large amounts of hot gas of the temperatures of 100,000 degrees and above, up to million degrees. So, this was an important addition to the two-phase picture resulting from thermal instability. So, apart from those two phases, which are produced by thermal instability, there is also a hot gas produced by the supernova. And here, in these plots, what is shown is the results of a simulation, a quite old simulation of 1999, which we did with Marit korpi. Also Axel was involved, and Ilkka Tuominen and Åke Nordlund. This is a simulation of the interstellar medium driven by supernovae. You have a box, and you inject, well, you start with hydrostatic equilibrium, homogeneous temperature, uniform temperature, as a thermal gas initially. Density stratified, you include density stratification, you include rotation in a sharing box approximation. And then you start injecting thermal energy in the right amount, 10 to the 51st ergs per injection, at quasi-random positions throughout your box. The result is horrible. The result is absolutely horrible, because what happens, you have these expanding blast waves. Locally, the temperature when you inject the thermal energy raises up to 100 million degrees. Depends, of course, on how big is the region where you inject the energy. But for simulations usually people make, it's 100 million degrees. Mach numbers are of the order of what, Fred? More than 100,000, right? Locally. Mach number of 100. These blast waves expand, but this is only the beginning of the problems. Because after a while, the two shock waves will intersect, and your code should capture the interaction of shock waves reasonably. So it's a horrible simulation. I remember when we first discussed it with Axel in Boulder, right? Axel, it was what, 1994? 1994.
Or 3, 4.
3. I remember we were sitting with Axel in a nice cafe on the roof under the warm sun, listening to the live rock music, really good. And I remember I mentioned Axel just simulating this sort of a stuff. This would be just a dream. So I said, why not? I didn't believe him. It took for me another pint to drink before I could continue asking him questions, because it was, at that time, it was impossible to even think about simulations of this sort. So, still, it's a great achievement. The very possibility to make such simulations is a great achievement, because it is a very demanding simulations. So, what we have here, so we drive this box in this way, and then this is the histogram of temperatures in the box. This is a histogram of densities in the box, and this is a histogram of pressures in the box. So, the histogram of temperature has two clear maxima, and the long tail here, density. It has a strong maximum here, a long tail to the right. So these two maxima in temperature correspond. Oh no, wait a minute. Yes. Here we truncated our cooling function at about 100 degrees Kelvin. Therefore, the cold phase here is represented by this table. The maximum is at 10 to the 4th kelvins. This is the warm phase. Another maximum is a million kelvins. This is the hot phase. The range of temperatures is from 100 to 100 billion. This is the sort of simulation you need to have with the dynamical range in temperatures of million, 10 to the 6th. Likewise here, in density, the range is from 10 to the minus 5th particles per cubic centimeter to 1 particle per cubic centimeter. Again, 1 million. Now look at the pressure. It has one single maximum pressure histogram. Look at the range. Just 2 orders of magnitude. This is a system which, despite the broad range of temperatures and densities, is roughly in the state of hydroequilibrium, of pressure equilibrium. These simulations, since that time, there were excellent models of this type. Miguel de Aviles had a very beautiful model, three-dimensional model, where he discussed also the interaction between the disk and the halo, because his box is much taller. It extends to 10 kiloparsecs above the disk. But his model doesn't include physically non-trivial magnetic fields. This was the first model with Marit, which included three-dimensionality differential rotation magnetic fields in full scale. It solves full MHD system of MHD equations. So this system is capable of maintaining dynamic action. In other simulations, until very recently, there was no other model of this type which would be able to support dynamic action. There were several models of this type which were two-dimensional. And two dimensions exclude non-trivial behavior of magnetic fields from the very beginning. Or there were models which didn't have differential resolution. Again, this affects magnetic field. And then, this is the derivation, the discussion of the supernova. This is the derivation of this Sedov-Taylor's solution. I think it's a typo here. Sedov and Taylor. Sedov published his paper in 1949. So they published it almost simultaneously. So this solution for the expansion of this hot bubble can be obtained just from dimensionality arguments. Suppose that it is an initial state of expansion where the expansion is so fast that energy losses are negligible. This means the cooling rate is much lower than the expansion rate. Then this means that the energy is conserved. It's an adiabatic case. And the solution, the radius of the bubble, will depend on the energy injected, density in the surrounding medium, rho naught, and on time. Just making dimensional analysis, you arrive to this solution, which is coefficient of order 1, and it depends on time of t to the power 2 fields. Differentiating this gives you the velocity of expansion of your shock wave. Very simple, beautiful, and useful solution. So this is just illustrations of how this solution looks. Well, density, this is the position of the shock front. Density increases, of course, towards the shock front, has a maximum shock front, and then drops to a very small value beyond the temperature, is the highest in the center of the bubble and decreases out, pressure increases out, and velocity increases. It's moving away from the center. This example is a pencil code. It's again, it's one of the tests which should be run. And I think it's one of the standard tests of the pencil code, right? Anyway, this is so that what is plotted here is temperature or density. Both will look similar. Density, okay, density. So you inject energy somewhere here. It drives two shocks which propagate outwards. It's a one-dimensional simulation. And this, the positions, the expected positions and values of density at this time obtained from Sedov solution. And this curve is what is obtained by pencil solve. It's a useful test. So the code can really capture this expanding charge. More of these simulations will be presented today by Fred Jan, who continues this work and who will present his results. And Oliver, yes, is here, so I hope there will be more than this. But we shall discuss his results later. There is an interesting question here. Imagine this again. This is an expanding. I'm saying that this supernova explosions drive turbulence, right? When you say turbulence, almost implicitly, we almost always mean vertical turbulence, right? Like Kolmogorov type turbulence. But this motion, expanding spherical shell, has zero vorticity. It's a potential motion. How this potential driving can produce vertical turbulence? How vorticity is created in this medium? You can write out from, you can take the curl of the Navier-Stokes equation and obtain equation for vorticity. So what we have here, these are in fact terms very similar to what we have in the induction equation. There will be, this will be increase in vorticity when the flow is converging or diverging. This is basically the angular momentum conservation. If you have converging flow, the vorticity, the region will rotate faster. This is the vorticity stretching. If there is a velocity shear, vorticity can increase. This is the term which was mentioned several times in the previous days. This is the, what is called the baroclinic term. If pressure is a non-trivial function of rho, for example, if pressure is proportional to rho to the power n, then this term will be equal to 0. That's because then the gradient of P will be proportional to the gradient of rho, and this term will be 0. But if the pressure is a more complicated function of the thermodynamic variables, Then, in a rotating medium, this term can become equal to different from zero. Gradient of pressure can be non-parallel to the gradient of density. And this term will also create vorticity. It works like a battery. Candace Roganan was talking about electric batteries, which basically are based on the same, creating electric currents from this effect. Usually this term is very small, and usually, moreover, it leads to only linear growth of vorticity with time. So this is most often negligible. And Murray made quite a detailed analysis of vorticity generation, and she argued that this is the most important term, the vorticity stretching is the most important term in converting the potential flow driven by supernovae into vortical flow. What is shown here is the, I think it must be vorticity in kilometers per second per kiloparsec as a function of time. This term, dashed line, shows the contribution of the Baroclinic term, right? Baroclinic term dashed, yes. And this is due to the vortex stretching. So, indeed, at early times, at early evolution, the Baroclinic term does contribute significantly. Again, it's the same simulation of a box driven by supernova. And at later times, vortex stretching is stronger. Let's estimate of amount of vorticity we expect from interstellar turbulence in the same units. So I have the turbulent vorticity in the order of turbulent velocity, right, divided by the turbulence scale by order of magnitude. It's of the order of 10 kilometers per second divided by 0.1 kiloparsecs. This is the turbulent scale, 100 parsecs. This is turbulent velocity. It's about 100 kilometers per second per kiloparsec. About 100. What we have here, 10, 8. So still, even this mechanism, after 250 million years, still doesn't provide all the vorticity required. I think that the main mechanism for this vorticity is related to the fact that the shock fronts in the homogeneous medium will be curved. And curved shock, when it's not spherically symmetric, has non-zero vorticity. It's no longer a potential flow. So I think, but it's only my speculation again, that the main source of vorticity will be this generation of this on curved shocks. Yes?
What about Coriolis forces in the rotating frame?
Rotation is quite slow. Rotation is quite slow. You want to generate vorticity at the time scale of millions of years, 10 million years, right? If you cannot wait 100 million years to produce your vorticity. And the typical time of rotation period, is 250 million years near the sun. It's too slow, I think. And plus, how to convert this large-scale rotation into small-scale vorticity. It's not also non-trivial. Even if the angular momentum is around, just transferring it to small scales is non-trivial.
But if you look at a remnant expanding into a medium that's inhomogeneous with clumps, then you easily get...
Yeah, this is what I'm saying, yes. Then immediately the shock front, the blast wave, will no longer be spherically symmetric, it will start curved, and these curved shocks, if you calculate the vorticity, it will be significantly non-zero. This is what I think is the main source of vorticity.
So that is vorticity produced by Baroclinic parabolic cross parabolic.
Yes. Yes, it is this curve. And it falls short by an order of magnitude of what you need. It's a violent medium, you know. And again, you know, the advantage of these interstellar things is that there is everywhere brute force. You have these expanding shocks which are curved. Unfortunately, I don't have a this is exactly where a movie would be useful, just to see how horrible and asymmetric it looks. But Fred will be showing movies from his runs. You will see how these certain symmetric shocks immediately become very strongly distorted. All strange shapes are there. So, in 1999, in our papers, we didn't discuss dynamation because we were absolutely unsure if we have it in the box. Our runs were relatively short and we didn't have time to have many runs, but Mara, in her thesis, she included some results which indicated that possibly we did have dynamo in our box. What is shown here is a thermally stable case. What is shown here, this is RMS energy, I think. This is the RMS magnetic field, and this is thermal energy. All these peaks are the supernova explosions. Each time you have a supernova explosion, here probably several of them exploded together to make a big peak. Every supernova explosion injects some kinetic energy and some thermal energy. Each small peak here is one explosion within your box. And this is the behavior of magnetic field activity. So, on the one hand, it doesn't decrease, but I wasn't sure at all if this indeed is a dynamo action. And we were unable to convince ourselves completely in that. But what Mara did for her thesis, these results were never published completely, she made a scatter plot of the electromotive force in the y direction. Y is the azimuthal direction in the box, versus magnetic field. And in the northern hemisphere, it looks like this. In the southern hemisphere, there's roughly some correlation, which is consistent with the idea they have the alpha effect, positive with alpha positive in the northern hemisphere and negative in the southern hemisphere. But and alpha of the order of 6 kilometers per second. Equality sign here is missing. Yes, perhaps this is true, but still, I always regretted that we were never able to finish and to continue these simulations. Basically, we had a running code, but running code isn't the result. Running code only means that we have a tool to start the work. It's the beginning of the work rather than the end. So, and here, for various reasons, we were unable to continue this work. But there were recently excellent results by Oliver Gressel and Ulla Ziegler, Detlef Felsner, and Günther Rüdiger, who had a similar model, but they succeeded in showing very convincingly that indeed the system is a dynamo. So this is a direct demonstration that the compressible, strongly compressible, random flow driven by these explosions can drive the dynamo. What was done here with the Nirvana code written in Potsdam? Here, the cooling function is thermally unstable. It includes lower temperatures, cooling at lower temperatures where the thermal instability kicks in. And the main difference, apart from this, from Marit simulations, is that the just larger value of the rotation rate, larger shear, of course it will help the dynamo. It will be easier to observe the dynamo. A very absolutely logical and good idea. And then the results were analyzed using the test field method. So all the components of the alpha tensor and the eta tensor, turbulent diffusivity tensor, were calculated. Let's have a look here. I'm sorry for the quality, even I cannot read here. If I remember correctly, these are the components of the alpha tensor in the horizontal plane, I think alpha yy. So this is z. Z is negative, Z is positive here, Z is equal to 0 here. You see beautiful antisymmetric behavior. These are, gosh, no, I don't remember what was here. Although you definitely do remember.
That's the off-diagonal alpha.
This is, so it's pumping, off-diagonal alpha, again it's antisymmetric. And these are the component of the eta tensor, right?
Exactly.
Yes, and you see that unlike alpha, they are even functions, roughly even functions of position. So, of height above the mid-plane. This is great. So, you do have a box driven by supernova. The boundary conditions were the following. In R, cylindrical radius. It's a local shearing box, but the coordinate which analogous to R, there was a shearing periodic boundary conditions. In azimuth phi, it was periodic boundary conditions, and the upper and lower boundaries were open, right? You also had the open boundaries. So now it's an excellent results to study dentistry. You have now dentistry medium in your computer. So lots of prospects you can do it. So it is to me, it's a very important result. It demonstrates that the whole machine can work despite its absolutely extreme violence. It's extremely violent. There will be more of these results presented by Fred Jen, and I hope you will be also presenting something, right?
On Thursday you will present.
So I'm really looking forward to today's Fred's talk and then your talk on Thursday. Magnetic rotation stability. Another beautiful animal in this zoo. The statement is the following. An arbitrarily weak magnetic field can destabilize a differential rotating flow with differential rotation, which is stable according to this Rayleigh criteria. This instability was first discovered by Evgeny Velikov in Russia in 1959. And Axel, do I remember correctly? I think you were telling me the story that Chandrasekhar, he also included this instability discussed in his book, classical book of hydrodynamic and hydrodynamic instability, that he first didn't believe in the result, and then repeated the calculations and was amazed to see that the calculation is correct. I will explain the physical nature of the instability in a moment. It's really fantastically simple. I cannot believe that this can be true.
That's a paper, that's not the book.
It's a paper. The book was in 1961, right?
Yeah.
And by the way, there is another important reference. Edgson. There was a book on MHD, which is perhaps isn't used and referred to as often as it deserves. Edgson, he published in 1961, I think, a book on MHD, which contains. Now, I saw it more than once when he would, after a talk about something new, for example, like rotation MRI, he would say, gosh, you are representing as a new thing. It's in my book I published in 1961. And there are many results of that. So it's a really very good book. So, the main impact of this magnetic rotation and stability was in the physics of accretion disks, where since early 70s, it became clear that there must be turbulence in accretion disks. In order for the accretion disks to be as they are, with some significant accretion feeding the central active object, there must be turbulent transport of angular momentum. But since accretion disks are stable with respect to Rayleigh criteria, it was totally unclear what is the source of turbulence. I saw with my own eyes how for year after year, very clever people were struggling with the problem. And then, this magnetic rotation instability showed that you, with arbitrarily weak magnetic field, you can make this flow unstable. So, what happens is the following. Imagine that you have a differentially rotating disk. I will try to make a complicated diagram, so I have to prepare the blackboard carefully. So, a disk.
But there is more light on this side.
Oh, then you can have light everywhere. Perhaps in the whole city.
So that's a full light now.
Let's concentrate on the white blackboard. I have a disk which rotates in this direction and contains some magnetic field. And now I will consider two particles which are originally at the same position, but then, or neighboring, very close to each other. But then one of them, just because of random motions, moves slightly inwards. And the two are connected by magnetic line. They sit on the same magnetic line. What is important is that this disk is stable with respect to the relay potential. And in addition, there's an additional thing. I will require that omega, angular velocity, decreases with radius. For example, like this way now, that law would do. So, d omega by dr is negative. D omega by dr is negative. D by dr of omega r squared is positive. So, if the particle will move inwards, this means that, and angular momentum is considered, right? The angular momentum of the particle, omega particle r squared, is a constant. It's the angular momentum of the disk which increases with radius from point to point. But this point, which has some angular momentum, omega r squared, if it moves around, it conserves angular momentum. If the radius has decreased, right, omega must increase. If omega increases, this particle will start moving faster than this one. So after a short while, so time proceeds into that. After a short while, these red particle will go forward, correct? But they are still connected by the same magnetic line. They are connected by the same magnetic line. The distance between them increased. What magnetic field will do? It will start pulling it back, correct? There will be magnetic tension here. There will be magnetic tension. If there is magnetic tension, so a force directed this way, acting on the red particle, and directed this way, acting on the yellow particle. They will be restoring magnetic force. So, this particle will be pulled back against the direction of rotation, correct? So, this force will have a torque. It will try to reduce its angular momentum. So, the angular momentum of this point will be reduced. If the angular momentum of this point will be reduced, it must move where? Inside or outside? Let's make a sketch. So now, this is radius, and this is omega, decreases, and this is omega r squared, increases. So this red particle is now somewhere at this radius. Right? What else? Oh, this is good. This is good. Both light. Well, I expected that we have either light or moving black holes, but both. Yeah. So, this particle is here. Now, I pull it back. Right? This force has a non-zero torque. It changes the angular momentum of this point. In what way? It is directly opposite to the general rotation. It reduces, it tries to reduce its angular momentum. If it reduces its angular momentum, the particle must move down to be in equilibrium. The smaller radius. The smaller radius. This means that this red particle, in the next moment, will move further inwards. And the opposite will happen with this particle. This force will try to increase its angular momentum, and larger angular momentum means being further away from the center. So the yellow particle simultaneously will move on. This was instability. You have shifted this particle slightly inwards. As a response, it moved further inwards, and then further inwards, this creates instability. So what is unusual here, what is difficult to understand, what is counterintuitive, is that it's exactly this point. You pull the particle outside to the radial radius, but quite unreasonably, it responds by moving inwards. But this is the same experience. Gyroscopes in children behave in the same way. If you take a gyroscope, right? Okay. Again, in gyroscopes, it's just angular momentum conservation, which is a non-trivial thing. The angular momentum contains a cross product. This is what makes it unpleasant, unpredictable. With a gyroscope, and you push it that way, it doesn't respond as you expect it to do. It moves sideways, right? So, and however well you know the theory of gyroscopes, it cannot stop amazing you. So, here too, you pull it in this direction instead of move out. Also with children. You see that, for example, it's snowing outside and the streets are covered with ice, and you see this young gentleman or young lady who intends to go to school in summer shoes. And then, of course, you reasonably say that, well, it's not the right time to wear summer shoes. And this gentle action produces unexpected result. That the kid goes to the school barefoot. Right? So it's a similar behavior, just because there is a hidden law of nature which is not on the top of our memory, both with the kids and with gyroscopes, which controls the system. So here, what is important here? That this behavior of omega r squared, that omega r squared increases outwards, but omega decreases outwards. This is why this particle first will start moving forward. The fact that omega increases inwards will make, the exposition of angular momentum will produce this tension. But then, angular momentum, this tension, will, because of this tension, the angular momentum of this particle will no longer be considered. It will be changed by this tension. And this change of angular momentum is such, because of this inequality, d omega by r squared, that it will move further down. Calculations are simple. Like with all linear stability, the calculations are simple. For plasma physicists, these calculations are trivial, because they're doing hundreds of them every week. The mechanism is just, well, beautiful. And that it is really amazing that this mechanism was left forgotten for 59, 91, for 30 years, 40 years.
So what does Etchison say about this?
Sorry?
And Etchison was not feeling guilty?
Yes?
So the crucial role that the magnetic field plays is allowing the angular momentum to be changed.
Yes. That affects the angular momentum of the particles. It creates this link. Without this link, what will happen is this particle will move out, then it will return back, there will be some oscillations, and that's it. Because of magnetic field, because it tries to make a reasonable, gentle suggestion. Come back. The response is moving out. This is exactly how it should be.
But there is question how many particles should be hit out until one is falling on the center.
But this is a fluid. It's a fluid. It's all continuous, right?
What means fluid?
Means fluid.
For one particle to fall on center, the excess, this angular momentum should be
Transported out.
Yes. And
yes.
this means that many particles should be removed from the whole equation.
Yes. This is what happens. Because in fact what happens is that this instability drives turbulence, and turbulence stresses drive accretion. It's not just that this instability alone produces accretion. It just drives turbulence. This instability is indeed, since the source of instability is always there, as long as I have magnetic field, the system remains unstable. So this instability can feed turbulence. And this is what it does. It makes first the whole flow turbulent, and then turbulent stresses transfer angular momentum outwards, and the matter can fall down to the center.
Angular momentum outwards together with the mass.
No. This is the point. This is the point. The angular momentum, this particle has got rid of its angular momentum. It's now in equilibrium here. It has exactly the angular momentum required at this radius. Batteries are going low, British quality.
Yes, but the white particle receives this angular momentum.
Mm-hmm.
Yes, and it means that this particle is moved outside.
Yes.
And after there is needed next step to go further.
No,
yes,
but it will not end at infinity. It will not. Because before it will try, the flow will become turbulent, and this trajectory will become as complicated as you wish. It's not that I'm saying that this particle will go directly to the center. No. This motion will become turbulent, is what I'm saying.
But even turbulent disk should conserve its total angular momentum.
Yes. It will be transferred outside. But the density decreases outside. So the amount of mass here is smaller than the amount of mass here. There is a symmetry. And angular momentum, well, it's not frozen into the gas, right? It's not that if a given particle had a certain angular momentum, it will always have the same angular momentum. For example, one particle can carry huge angular momentum outside, and many particles can carry the same amount of angular momentum inside. So angular momentum can be redistributed between volume elements. No problem. It's not that one single gram of mass will not necessarily have always the same amount of angular momentum. It can change. So the amount of mass which moves out can be smaller than the amount of mass which moves inwards if the angular momentum can be redistributed.
Is it really so?
At least equations indicate
But
that.
the solution of the angular momentum equation with this diffusion, whatever,
Mhm.
if you start with some profile and some disturbance, you find most of the mass going in and the tail moving out, carrying
And
the
then the momentum going down.
So you can see this in any review article on accretion, this solution of.
So you can indeed separate a cat from its smile. They behave differently. Right? So, Axel, I know how to move the leg back, but how to remove light?
And or again, just to
side.
make this point
Yes.
clear, because I think this is a very valid point. It's just to make it clear what is conserved and what is not. What are you assuming is conserved
Angular
during
momentum.
the entire process?
Angular momentum is conserved.
Mass is conserved,
Of course, yes. Oh, of course, yes.
and the magnetic field is imposed from somewhere else.
Yes. But it can be arbitrarily weak. Here, I never made any reference to the strength of the field. Arbitrarily weak magnetic field will do.
I mean, you can just write down the angular momentum equation. You want to do that?
What do you...
And then you see that there's a flux.
What I mean is, the omega by d by dt of rho times, let me do it like this, omega is equal to a negative divergence. And now we have various terms, and so the most important one is the stress. And that consists of, let me get the sign right,
VR, V phi.
and that comes with a minus sign again. Yes.
And VR, V phi.
Yes. And then there will be another R factor and a rho and no rho factor. Is that correct? It could be additional factors. And then there will be another one, of course, which goes like this. And these would all be averages. No, I will do everything. And
there would be corresponding contributions from the large-scale fields, but that's the most important one.
And these are turbulent stresses, right?
Turbulent
Random
stresses, yes.
And the mass is conserved, no problem. Except for the sink at the center, if you want to introduce it as a sink.
So it's a transport towards the wall. Outer wall, if there is such a thing, will spin faster. The inner one, which is the central star, will slow down.
So, what do we have here? Yes, so this magnetic stability can indeed drive turbulence, and then this turbulence will drive magnetic field. These are figures from the simulation of Axel in 2005. So these are the components of the alpha tensor. Axel. There was no test field. It was used with test field method. I didn't know. Also only with the test field method. Sorry?
Yeah, I was wondering if it's...
But what is remarkable here is that the sign of alpha, YY, in the northern hemisphere is negative. That, let's go back. Here, the corresponding value of alpha is positive in the northern hemisphere. This is what people usually assume about the sun, the earth, and the galaxy. That this coefficient alpha is positive in the northern hemisphere, negative in the southern one. And here it's the other way around. It's negative here. In Axel's paper on 1995, there is an explanation of this, but I could never understand it completely. To me, it still remains quite non-trivial and interesting feature related to the physical nature of the magnetic rotation instability. So, and this is the turbulent diffusivity produced by the magnetic rotation instability. So, it's just a healthy, good, and pleasant dynamo. So, can this be important in galaxies? First, this, as any other such a continuous instability, it's a gentle process, right? Even if it behaves like a teenager, still they are gentle creatures. You know? It's easy to destroy them. Supernovae, of course, make this the development of this instability harder. And there were work of Marit with co-authors, with Petri, Kapila is involved in this work, about the development of magnetic rotation instability in a disk which has supernova activity. What is shown here is that this is omega for the flat rotation curve. It behaves like 1 over r, and then it's just truncated here. This dashed curve is the growth rate of magnetic rotation instability. And this solid curve is a damping rate of magnetic rotation instability connected with the turbulent diffusion produced by the supernova-driven turbulence. Okay, let's forget about the central part, because here anyway we have truncated the omega, so it becomes unreliable. But so this is the generation growth rate and this decay rate. The growth rate of magnetic rotation stability becomes larger than the decay rate beyond the radius of about 14 kiloparsecs. And about the same radius, 16 kiloparsecs, the supernova activity ceases at all. And at this radii, the magnetic rotation stability seems to be the most, perhaps the only source of turbulence. And remarkably, many galaxies, including the Milky Way, can be observed out of very large radii, up to 50 kiloparsecs, which is 5 times further away from the center than the Sun. In neutral hydrogen is so abundant that the signal is still strong enough to observe neutral hydrogen at very large distances from the galactic center. And remarkably, even at those distances, where there is no star formation, no supernova activity, still the gas remains turbulent. Perhaps this is what drives the turbulence. Moreover, there were results which are still very speculative, observational results, which indicate that perhaps large-scale magnetic field extends also to the very large distances from galactic center. Rainer Beck in Bonn is an active proponent of this viewpoint. what they did, they observed the Andromeda Nebula at large radii. The galaxy itself has a very nice magnetic field, which is readily observed. But these people observed the Faraday rotation from the background sources at large distances from the center of the galaxy, definitely beyond the visible disk. And the number of the sources was relatively small, something of that sort, half a dozen. But they showed that all these sources have Faraday rotation measures consistent with each other. Say positive on this side and negative on this side. It can be coincidence. With a small sample, it can be coincidence, but maybe not. If it's not a coincidence, and such results can be confirmed by more statistically reliable analysis, then this indicates that magnetic field, large-scale magnetic field, is still maintained at large radii where supernova activity is just absent. There are no supernovae there. Again, this perhaps will make this idea of magnetic rotation and stability much more important. I simply don't know. This needs to be. Yes?
There's two comments. One is that because MRI operates on the rotation time scale, and the supernova operates much faster in the inner regions.
What do you mean? I think that the growth rate of magnetic rotation stability is all in speed times k, right?
No, it's omega, related to just the rotation rate.
Okay.
So the rotation rate in galaxies is much smaller than the time scale for studying by the supernova.
Yep.
So I don't think it's important at all inside. Forget about damping this. That.
This is what I'm saying.
No, forgetting about damping and growth, it's not at all fast enough inside.
Oh, why not? Why not? Oh, for example, the mean field dynamo operates on the time scales much longer than the turbulent scale. Still, we are talking about slowly growing large-scale field.
Constantly stirred all the time by the supernova and the fluctuation dynamo. It is, as a source for turbulence, it's like saying that you have something 10 times larger and something 10 times smaller.
Yeah.
And as a source for turbulence, forget about whether it can damp. I don't think it can be there at all.
Okay.
This is the first comment. The second comment is on the outer regions. There's a very interesting recent paper by Klesson and company. Klesson is one of the authors. I just wrote because he mentioned it. So they argue that for many galaxies, you have accretion in the outer radius from the intergalactic medium. That can drive the turbulence. It's a preliminary thing. It's an interesting thing to just watch out for.
Can be. Yeah. Agree, yes. There can be more than one source of turbulence in the outer
especially because nowadays you get all these simulations of structure formation which show that filaments are kind of landing up onto galaxies.
Oh, the structure formation, I would be a bit careful, because what is the size of those filaments?
Okay, whatever you resolve, not the supercluster scale things. On individual galaxy scale, there are filaments which are landing up in the outskirts of the galaxy. And there are cold flows which are landing up in the outskirts of galaxies. So, while you should be careful, but
you know, the problem here with such mechanisms is generally that it's not clear what this will cause. Will it drive turbulence in the disk, or it will destroy the disk entirely? Because it's very easy to overdo the things, right?
yeah, absolutely.
And so that you want to drive turbulence, instead you can destroy the disk. This stuff works in the disk. It will definitely keep the disk intact, right?
Agreed,
Meanwhile, all these filaments coming down, they can just destroy the disk instead of driving turbulence in it.
yes, but
Because gravity is relatively weak there.
And you can't do anything.
Yeah, agree. I'm not saying that it's the only and firmly established source. No. I'm just talking about possibilities of interesting
All I'm
physics.
saying is the reason for MRI to be interested in accretion disk is because of the rapid shear time scale in accretion disk. The reason for MRI not to be so interesting in galaxies is the very slow shearing rate of galaxies.
Yes. But still, if there are no other sources of turbulence, this can be important.
Yes.
This is the statement of Murray, with which I agree.
what about the vertical direction? Do you think MRI can be important in the halo?
Why not? Everywhere, if you have rotation. Absolutely. Absolutely. Maybe but in the halo also there are some supernovae. There is this, if these particle loops are indeed important, that there are some ideas how turbulence can be driven in the halo. But indeed, it can be a dominant source of turbulence there. Yeah. So what happens with radio? So, what else? That's all. Perfect timing, right? Absolutely perfect timing. Thank you.
Thank you, Anwar. Only now I remember that we forgot the microphone, but I hope it was not too important. Questions, please.
So it will be a silent movie, right?
It should be. Really quick. But you had difficulties hearing? No. Anwar has a good voice. So, any further questions? So what do you think will be the next important steps in those directions in order to clarify the nature of turbulence further? Will one need to go to global simulations? Will one still be able to learn something from local simulations?
Yes. I do think that these local simulations in a sharing box have enormous potential. There are many things to do. But on the other hand, it would be useful simultaneously to move, perhaps gradually, to larger scale simulations. We were discussing with Fred and Andrew Fletcher and Graham Sarson that perhaps given good computers, we have access to good computers, first to consider, say, 1/4 of a circle, or even 1/8 of an annulus would already be nice to see. Because effectively, especially if you want to consider the large-scale magnetic field, this would be important. For discussing fluctuation dynamo in the box, which is also a very interesting question. You don't need global simulations for it. But for the large-scale magnetic field, especially non-axisymmetric field, so moving towards global simulations would be important. But it will be very slow progress, obviously. The progress is going to be very slow. But there are, right, models without magnetic fields of global simulations of this sort.
There is even one or two with magnetic fields. The group of Michael Hanasch are doing global simulations now, and there's a French group, Giesinger and
Yes,
more.
yes. But there, yes, it's with Emmanuel Dormy, yes. But there, the problem is that they model the supernovae not by injecting thermal energy, but just kinematically introducing the diverging flows. This means that this model kinematically is okay, but thermally no. So there is no multi-phase structure. And this stuff, the interesting aspects of this is exactly this multi-phase structure. How this multi-phase structure affects dynamo action. Because unlike the Sun or the Earth, here we have the dynamo action, a system where density changes from one position to another by a factor of million. And temperature likewise. So we have very little intuition. Which would guide us when deciding what can happen in such a system. Plus, it's an open system. Yes, Tamara?
Yeah, also it's important to check in all these cases whether you have a slow dynamo or a fast dynamo, because I do remember in the cosmic ray-driven dynamo simulations in Hanasch, and I don't know what is the situation yet, but if you decrease the microscopic or whatever resistivity, whatever they use, then the growth rate seems to decrease or something. So you have to be a bit careful.
Okay, it seems that in the simulation of Michal Hanasch, the
Yes.
numerical diffusivity is continuous.
Yes, I did check on this, and it seems to be a fast dynamo for the case where you drive thermally. But I couldn't get to really high Reynolds numbers.
Right.
But what I remember we were discussing it with Michal, perhaps what is difficult to understand, what happens with magnetic helicity in the box, because his dynamo works with closed boundary conditions. This probably means that viscosity, magnetic diffusivity, is so high in the box that the magnetic helicity is just destroyed locally. which can affect the nature of the solution quite significantly. And again, it's nice to have this cosmic ray-driven dynamo, but this violence of expanding shells, it can affect very strongly also, right? Like MRI-driven instability. What can you say about that?
Yes, I definitely think that cosmic ray diffusivities might be strongly suppressed in a turbulent scenario because they are highly anisotropic with the field lines. So if you have tangled field lines, that might not work at all.
Yeah, but Michal already uses the high turbulent diffusivity for cosmic rays, consistent with observations, which cannot be reproduced by the code automatically. It's just there termed in the equations. This is perhaps okay, but just the molecular diffusivity, ohmic diffusivity in his code is probably very high. So the question what happens with helicity in his dynamos remains open.
The other issue which I got raised when I was talking to Lesson about some of this is that in the fluctuation dynamo, how correlated is where the field is with where the density is advanced. So that, for the guys who are doing star formation, they want to know, even if you have, right in the beginning, if you have no mean fields, they have this fluctuation dynamo, which is generated blocks of stuff. Does the magnetic field affect the star formation? So even in your box, it would be interesting to see this correlation between where the field is from and where the density is.
Yeah, we discussed it with Murray, and then with Grahamshausen, and there is no clear correlation, at least in the runs we have, there is no clear correlation between B and rho. It's by far weaker than what we expected. But it's an open question because it can be due to many different reasons, also of numerical and artificial nature. Here, there are almost infinitely many questions of this sort which you can address even with local simulation. But still, it would be a dream to have another dream, to have the move towards global paths. This would be great.
Do we see significant winds vertically outwards?
Yes, winds are becoming more and more fashionable, definitely in young galaxies. Definitely young galaxies, which are, when they are formed, there is a burst of star formation. And which can drive a wind, also cosmic rays, or the cosmic ray pressure, it can drive wind that is a flow which extends to infinity. But in mature galaxies like the Milky Way, probably there is no wind. There is an outflow from the disk, but it doesn't extend to infinity. It's a galactic fountain. It's just a sort of convection type flow around the disk. Now, quite often people start mixing these two terms. They call wind, every outflow from the disk is called wind. I think it's very confusing. The wind is a flow which extends to infinity. The flows which don't extend to infinity mustn't be called wind. But people are very often mix the two. So I think that in mature galaxies, z equal to 0 now, winds should be relatively rare among spiral galaxies. But in young galaxies, they should be a rule rather than an exception. Still, in the nearby universe, there are many galaxies. M82, for example, it's a starburst galaxy which has very intense star formation. And most probably it has a wind extending to infinity.
They are never collimated, right? Unless you are talking about an AGN.
This sort of an open thing, this sort of outflow. Comparable. The opening angle is quite consistent with the geometrical dimensions of the galaxy.
Could you expect that the MRI drives a dynamo so that the whole thing be self-sustained?
In galaxies?
Yeah. You could start with a magnetic field, change the velocity profile.
I don't know.
Get a dynamo prone. It seems that it's an observation that was made in a run by Fausto Cataneo a couple of years ago.
Quite low, yeah.
In the inner
Or
part
the
of
MRI cut the source off and the field wouldn't go away.
in the inner galaxy, you don't need it. There are other sources of turbulence, which is, I agree with Kando, which will make MRI in the inner parts unimportant. Okay. In the outer parts, I cannot answer your question because I need to take an envelope or napkin after the lunch and make a couple of estimates. Because there, in the outer galaxy, the problem will be that rotation period becomes very long. Rotation becomes progressively slow as you move outward, and this can kill this enemy. So I need to make estimates. Definitely, there will be the outer radius beyond which dynamo action is impossible, just because the time scales are unreasonable. Where is this radius with MRI? I don't know. But it can be just a few simple estimates, and you will have a rough idea of it. But I haven't made research. I haven't done research.
It helps to have a very thick disk in outer region. Then your dynamo number becomes better, but your time scale slow down. So this was the fast estimate which I was trying to make with lesson about this stuff.
Yeah, there is always, you need to find optimum. There will be some factors will be helping you, the others will be making your life harder. If you're lucky, it will work. If not,
I mean, that's what Anwar basically showed, the MRI simulations, which do show both an alpha effect, but they also show dynamo action of large scale type. And the alpha effect has the unusual sign, yeah. So there's a strong belief that an MRI should work generally. It's just a question of whether it will be strong compared to the supernova-driven dynamics.
and plus that time, again, in accretion disk, rotation is very fast. It's not a problem. Rotational time scale is very short. In galaxies, especially the outer parts, I agree with Kando, it can be limiting factor. But this should be quietly and without too much excitement explored.
Right? Is there no further questions? Then we break for the break. But there is the opportunity to have a conference picture, or the school picture. And that would be up just before lunch. So like 12:30, 12:30 to 12:40. And that will be in the staircase here, between here and the kitchen, between here and the cafeteria. So 12:30 or after the...
Another option is to make it here, right?
No, that's...
Another option. And this black background will be good for pictures.
Then we need to sit on the same...
Yeah, but it's easy for everybody to get.
Yeah.